Assalamualaikum and good day everyone. Today we are going to talk about the introduction to differentiation. First, let us start from something familiar. The slope of a straight line. So the slope of a straight line is calculated by using the formula of rise over run. As you can see, for a straight line, the steepness never changes. It is constant everywhere. Doesn't matter if you calculate the slope at this point, or maybe at this point, or maybe at this point, you should get the same steepness or the same slope. Now, let's look at a curve. Curves change their steepness at different points. One point can be almost flat, another part steeper, another part might be very steep. So, we need a way to measure the slope at a single point on a curve. So we have differentiation as a tool that will help us to do that. Because we can't rely on just a single formula that is actually applicable only for straight line. Now, to find how steep the curve is at a point, let's say point P, on a straight line, we are going to choose 2 points. So we are going to have point P and another point is point Q. So for point P, we are going to have the coordinate of x, fx or xy. And for point Q, right, by considering the horizontal change or denoted as h, so we are going to say that Q is actually equal to x plus h and also fx plus h. With that in mind, we can now draw a straight line between them. This will allow us to use the formula of rise over run to find the slope for this line. And what we are going to get later is actually we are going to get the average slope of Q and P. And if we try to be more specific, we can write down the formula as slope equal to rise over run, or based on this coordinate, we can also write it down as slope equal to the rise, which is f x plus h minus with f x, okay, which is this minus with this over with run. So for the run, it's actually x plus h minus with x. So x plus h minus x. If we try to simplify it down, you will see that we will get fx plus h minus fx over with, we cancel out the x, it will leave us with h. Notice that this formula is actually similar to the formula of first principle shown in our textbooks in page 131, which is this one. But we just still look at this. We still haven't come to the point of how we can get this limit h approaching to 0. Now, please bear in mind that we have been clear that this formula alone, right, the formula of rise over run alone is not enough to be used to calculate the slope for curve. It's only ideal for the slope for straight line. So why do we still calculate this? Right, it is because we are going to need to do some extra steps in order for us to apply the rise over run into a slope that is actually in a curve graph. So let's look at this. Now, the one that we did until now is actually calculating point P and point Q. So because of it is actually far, we can say that the average slope provided by this calculation is not accurate for the point P that we want to the slope of for point P that we want to look at, because this actually gives a slope at this point which is not accurate to point P. So what do? So we need to actually make it so that Q and P, right, become close to each other. When the P and Q is far away, we can say that the slope is inaccurate. But when the Q is closer, the slope calculation or the slope estimation is actually improved. But it is close, become the slope become closer and closer to actually representing the slope at P, but still not enough. So we still need to make it become extremely close. When it becomes extremely close, it is actually, we can say, nearly measure the slope, the true slope of P. So this idea, bringing Q close to P until they are kind of overlap to each other, is actually the foundation of differentiation. What happening in this whole process is actually we are shrinking the h, right? This, right? This, right? The h here is being shrank. So in mathematics, right, this process here, right, is being denoted as LIM, which is the limit. We let the limit of h to approach 0, very near. Actually, we let the P and Q become very close so that the h is almost the difference is almost 0. That's how close is it. So later on we can assume that h is 0 when we do the calculation. Hence, that's why firstly we have this formula, and then later on we added this, right? And this whole formula become the complete formula of the first principle of differentiation. So by looking at this first principle of differentiation, it literally means that it finds the average slope between the two close points, and then bring the points extremely close, and using this calculation you get the final slope, which is the derivative. Now let's try to use this formula, right, to differentiate fx equal to x squared. So to differentiate fx equal to x squared, we know that the other point is x plus h. So basically the equation here is also will be changed to x plus h, right? We add some distance from x, so x plus h squared being expanded to become this. Later on, right, we're going to substitute it in this formula. So we have fx plus h, which is this, minus with fx, which is x squared. So this x squared will be cancelled out, which will leave us with only 2xh plus h squared, which is this. Carry on with the formula of over h. Later on, the next thing to do is to cancel out the h. So that will leave us with 2x plus h. And then from this 2x plus h, we have the limitation of h approaching to 0. So we are going to assume that h is 0. So substitute h is 0 into this equation, and that will just leave you with 2x. So basically the differentiation, the derivative of x squared is 2x. Now for those who have experience in differentiating, those using power rule, alright, in differentiation, you will see that this is actually quite a handful of steps that we need to do before we able to get 2x from x squared. So basically, okay, the first derivative did shows us how derivatives are created, but we don't want to use the long method every time. So that's why mathematicians created simple, powerful rules to differentiate quickly. So we have rule 1, which is constant rule. It is a situation where you have a constant, right? So we want to differentiate it, and constant don't change. So basically their derivative is actually equal to 0. So every time you differentiate a constant, it is equal to 0. Next, we have power rule. So for power rule, every time you encounter with an equation that contains power, you will need to make sure that the exponent, right, the exponent need to put it on the left side here, and then the power needs to be reduced by 1. So for example, x to the power of 3 become 3x to the power of 2. X to the power of 10 become 10x to the power of 9. Reflecting to the problem that we solved using first principle just now, right, which is x squared. Using the power rule, we can easily solve it, right? So basically we can get the derivative of it is actually 2x. So that's how easy the differentiation when we just remember the rule instead of using the first principle. Next, we have constant multiple rule. This is where it is actually a mix of constant rule and power rule. So basically, when you have a constant rule with we have a constant together with equation with power, always pull the constant out and then differentiate this using power rule and then multiply it back. Okay, so that's how you deal with this kind of problem. Next, we have sum and difference rule, right? There's nothing much difference. So basically it just talk about how to differentiate an equation that have sum and also subtraction. So basically to do it, just differentiate each term separately. For this case, let's say you have fx plus gx, so just split it up and differentiate them separately. So for example, x to the power of 3 plus 4x. So first differentiate x to the power of 3, you get 3x squared. 4x become 4, and then you put them together, you get 3x squared plus 4. The same goes for this one, right? We differentiate them separately and then put them back together. So that is for sum and difference rule. And lastly, let's look at the derivative of simple polynomials. Okay, combining of what we have looked until now. So let's say we want to solve 3x to the power of 4 plus 5x to the power of 2 minus x plus 7. So for 3x to the power of 4 become 12x to the power of 3, and then 5x to the power of 2 become 10x, and then we have negative x will become negative 1, and then 7, which is a constant, becomes 0. Just put them all back in, so you will get this final answer. So basically that is actually what being covered in the introduction in differentiation. You now understand how derivatives are created and how to use basic rules to differentiate quickly. Thank you.